All right, everybody. So what we're going to be looking at today is part two of the lecture that we started yesterday, which was on the dot product. But today we're not talking about the dot product in particular. We're talking about vector projections. So these are very, very useful. Okay, so we use these a lot. You'll use them in other classes, physics classes, engineering classes, things like that. Um, yeah, they're a very useful concept. So the idea is this. So suppose we have two vectors here. I'm going to draw one like this, and let's call that one V. I want to get the names right, by the way, because otherwise everything will be reversed in the definitions. And then you have another vector down here, and let's call that one U. Okay, so these are just two different vectors that I'm showing in space. And something that's very useful to know would be how much of V is in the direction of U. I'm going to write that down. So how much of V is in the direction of U? Okay. And what do I mean when I say that? Well, what I mean is this. So if you come down here on this picture and you draw a line perpendicular to U that goes to the terminal point of V, so like right here, like that. So this is a right angle. Then where that line touches U right here, this is the thing we're talking about. What is that? And there's two questions you could ask about that little vector that I drew there, the pink one. You can say, first of all, how long is that? And you could also say, what is it as a vector? So how long is that third vector that I drew? And also, what is that vector? Okay, so that's what we would like to know. And you can do something with trigonometry to figure out what that is. In fact, let's see if we can do that. I didn't do it ahead of time, so hopefully I can do it right here. So let's just look at it. So if you wanted to calculate this, then what we would need is to think of a triangle here, right? So there's actually a little triangle here, right? If you think of that as a triangle, then you've got a V here. You've got this. Make sure those line up right. And you have this. And this is a 90-degree angle, right? And the only thing we know is that we've got the V here, but also you've got this theta. And the theta there is going to be the angle between the vectors U and V, right? Even though like the angle between the vectors V and U is also the angle between the vectors V and whatever this one is that I didn't give a name. In fact, though, let's give it a name so I can stop writing a question mark there. What we're going to call this is we're going to call that the projection of V onto U. So the U is like a little subscript there. And I'll explain the notation in a little bit more detail in a little bit. Okay, so first thing we can do is we can figure out how long that side of the triangle is, right? And so if you think about trigonometry, with a triangle like this, that the right side of the triangle here, you can't see where I'm pointing, right here, this side of the triangle would be magnitude of V times the sine of theta. And this side would be magnitude of V times the cosine of theta, right? So like if V was 1, then the sides would be sine theta and cosine theta. And that's pretty basic trigonometry. I'm not going to go over that. I'm just going to, state it. Okay. And that really gives you what you want, at least something that you want, because if you want to know how long this vector is supposed to be, well, now it's this, right? Magnitude v cosine theta, that's the length of it. So we just discovered this fact. So we just discovered that the magnitude of the projection, what is it, of v onto u is equal to, well, the magnitude v times the cosine of theta, where theta is where I drew it in the picture. Okay? But now the question is, what is the cosine of theta? Right? So if you think back to the previous lecture, we had a certain thing, right? In the last lecture, we wrote this, that the angle between two vectors is u dot v, remember, was equal to magnitude u, magnitude v, times the cosine of theta, right? So you could actually work this out, and you can solve for, hey, get out of the way. There's a notification on my screen that you can't see, but it's annoying me. Okay. What you can see here is that v cosine theta, sorry, magnitude v cosine theta is actually right here, right? So if you want to solve for magnitude v cosine theta, you just have to take this magnitude u and move it over to the other side. And so when you do that, you get that magnitude v cosine theta is equal to u dot v over magnitude u. Okay? So then you can take that, and that is what this is equal to, which means that is what the projection is equal to. So this tells us a fact. Therefore, the magnitude of the projection of v onto u is equal to u dot v over the magnitude of u. Okay, so that's the projection, magnitude of the projection. Okay, but if we want to know what the actual vector is, right? So this is the length of that projection, the length or magnitude of the projection. And how would you calculate the actual projection itself? So you have to, oops, writing too many words. You have to think back to how we found vectors that were unit vectors and vectors that were a certain length in a particular direction, right? That's a problem that we solved. So what you would want is the projection of v onto u should be, well, what do we know? We should have the magnitude that we want, right? And then you should multiply that by a unit vector in the direction we want. I'm going to rewrite that so you can read it. Unit vector in the direction we want. Right? That's how we did it in the previous sections, right? 2 sections ago, we were already doing that. The magnitude we want times a unit vector in the direction we want. But guess what? We know both of these things now, because the magnitude we want is what we just calculated. So it's going to be u dot v over the magnitude of u. And then we have to multiply it by a unit vector in the direction we want. Well, let's look at the picture again so we can see what direction it is, right? So the projection of u, sorry, projection of v onto u is this pink vector, and you can plainly see that the pink vector is in the direction of u, right? It's supposed to go in the direction of u. So what we need is a unit vector in the direction of u. And we know how to get a unit vector. You take a vector and you divide it by its length. Right? So you got these two pieces, the magnitude we want and a unit vector in the direction we want. Multiply them together, and that is the projection of v onto u. Now, this can be simplified a little bit here. You can write it like so, projection of v onto u. And what you want to notice basically is that you've got a magnitude u in the denominator here, and then you've got a magnitude u in the denominator here. So you just basically move this one over, and you can write this as u dot v over magnitude u squared. And then you still have this leftover vector u, like that. Okay, so this is one way that you'll see it. Also, you might remember what is the magnitude of something squared, right? You might remember that, might ring a bell. And, you know, think about it for a second while I'm scrolling up to make sure I don't write something dumb. The magnitude of a vector squared is just the dot product of the vector with itself. So you could actually write it this way as well. Oops. This way as well. U dot v on top, u dot u on the bottom, and all of that times u. So this right here that I'm putting in parentheses, that's a number, right? A number times the vector u. Okay, so that's it. Okay, so let's summarize this. So what you need to remember forever, but what you need to remember is this. So what we're going to have is what we call the vector projection of v onto u. That's this projection v onto u. And it's what we just wrote down. So u dot v over magnitude u squared, u, or if you want to write it with a bunch of dot products, u dot v, u dot u times u. And you got to really work hard to remember this. Everything here is a u except for this one v, right? U. 4 u's and a single v. So just be careful that you remember that. That can actually help you remember, by the way, right? That there's one single v there when this is a v. Okay, everything else is a u. Now that's what we call the vector. Oops, I just erased a bunch of things. That's what we call the vector projection. Now, the reason I was writing that is because there's another thing that we call the scalar projection, and it's just the length, the thing that we calculated first. So the scalar projection of v onto u, and you can write it a couple of different ways. They write like component. They write like this, C-O-M-P V onto U, like that. And by definition, it's the magnitude of the projection of V onto U. And we calculated it already. It was that up here, this thing, U dot V over magnitude U. U dot V over magnitude U. And again, there's only one V there, right? So only one V. And, you know, I'm doing that to hopefully make it easier to see what variables you have. So that's the scalar projection. And it's that length. So on our pictures, I'll draw the pictures right here so they're just next to it. Right, U could be there, V could be there, and there's two things to calculate. There's first of all this length. That length is what we call the component. Let me just actually duplicate this right now before I write on it. Put it over here. So the length here is the component of V in the direction of U. And if you actually write it as a vector, it's the projection of V onto U. Okay, and so that's the notation, and those are what the pictures are. So this one's a number, and this one is a vector. And so those are very useful things to be able to calculate. They do come up a fair bit. All right. So let us see if we can calculate some stuff, right? So let me scroll down a little bit here and let us calculate this. So here's an example. Hopefully it won't be a dumb example like happened yesterday. Let's see. They just say find the projection of V onto U. And they give us, what do they give us? Two vectors, obviously. So the vector V is 3, 5, 1. And the vector U is -1, 4, 3. And so we want the projection here. So how could we do it? Well, you could break it up into two parts where you separately find the scalar projection and then turn it into the regular vector projection. Or you can just start with this formula or this formula. So whichever one, I'll do this one. I think that's going to be the least amount of work. So I say, so here's my answer. The projection of onto U of V. It's really easy to get that backwards. So make sure you try hard to remember this, or more likely just write it down, right? So remember how it goes. If you're projecting V onto U, everything is a U except for one single V, right? So it's going to be U dot V, U dot U, U, right? So everything's a U except for this single V. Okay. So this is not actually that hard to work out. We just put everything where it goes. So you got U dot V 3, 5, 1 over U dot U, which is -1, 4, 3, -1, 4, 3. And then all of that is times the vector -1, 4, 3. And that's what you're going to calculate. So it's really just two dot products and then one multiplication. So it's not actually as hard as it might like appear at first. So on top, we're doing this dot product. Dot products are easy. So you got -1 times 3 plus 4 times 5 plus 3 times 1. And then in the denominator, you've simply got -1 times -1. So -1 squared plus 4 squared plus 3 squared times -1, 4, 3, like so. Let's work out that numerator there. So we got -3 plus 20 plus 3 over, what do we got? 1 plus 16 plus 9, -1, 4, 3. So you work out that numerator. Of course, it's just 20. In the denominator, what do we got? 26. Is it just 26? Negative 143. Um, yeah, and then you can work that out. So this right here is also right. It's 10 over 13 is that fraction. So if you multiply that out, it's negative 10 over 13 times multiply that by 4. It's 40 over 13. Multiply it by 3. It's going to be 30 over 13. So you work that out. Okay, and then that is your vector projection. Okay, so that's how you calculate them. Not so bad, a couple of dot products. They seem harder than they are because the formula looks pretty complicated, right? Um, but when you actually get down to it, it's pretty straightforward. Now, I don't know what resources you have that can do vector projections easily. Uh, Maybe we'll go try to find one on Twitter. Let's try. Let's see if Wolfram Alpha can do this. I don't know, so just keep that in mind here. What are we trying to do? So we want project. What are we trying to project? 351, 351 onto negative 143, negative 143. Now, I don't know if this is going to work. We're going to find out. It might not even like our vector notation. All right, yeah, there you go. So, yeah, you can make Wolfram Alpha do that. So that's nice. The input here, that's how you were supposed to type it in, but I didn't, right? Because I didn't know how to type it in. So I just typed it in. Yeah, and you can probably do this. Maybe I can try scalar projection of. It might not do this. Nope. See, you didn't know it. But what you could do is, oh well, it would help if I spelled it right. But what you can do is there's different ways. First of all, it might be called the component, right? The COMP notation that you saw. So you can try that to see if it understands that. It doesn't, right? So, switch back to projection. I would probably do it this way. So since I don't know how to do it, I can do this, right? And then it gives me the vector right there. And since it gave me the vector, then you can just say, magnitude of, and then you can write it like negative 10 over 13, 40 over 13, 30 over 13. That's a 14, like that. So there you go. So you could get it that way from Wolfram Alpha if you so desire, but it would take 2 steps. The point that I was trying to make here is that Wolfram Alpha, if you haven't been using it before, is a very good site for doing calculations for a class like this, just to check your answers and stuff like that, pretty much. Okay, so let's go back here. All right, I gotta close that again as per usual. All right, projections, and we're back. So that's what a projection is. Now, why do we care? So you use these in physics a lot to do a certain type of calculation. So let me do an example here. So these are used in physics. I shouldn't say these, I'm going to say projections. Projections are used a lot in physics. That's not how you spell physics. Physics. All right. So like here's an example. So they get used for forces a lot of times. So example here, they say like, let's see. They got a little wagon. This is their picture. So you have a little wagon like this, and then you've got the handle of the wagon, right? And um, so if you have a child pulling on the wagon, they're drawing this force this way. So you have a force vector pointing in that direction, right? And then they say something like they say, if a child pulls the wagon with the handle at a 55-degree angle, how much force is in the direction of motion, which I didn't draw yet, right? But presumably the idea is that the wagon is going this way, which I don't want to draw it there. I want to draw it. Let's draw it here. That makes more sense, right? That's supposed to be horizontal, so I'm going to try it again. So this is direction of motion, right? And the way that you would want to calculate this is you also have your angle, right? So if you want to know how much of the force is in the direction of motion, what you're looking for is a vector projection, right? Because you simply bring this down here like this. There's that angle. And then you've got this right here. And what is that? Okay. So basically what you would be looking at is the vector projection. It would be the projection. Let me actually give this a name. The direction of motion. What is that vector, right? So F is the direction that I drew it. That angle. This is F pointing this way. What is this? We just need to give it a name. Let's call it like D. Okay, D for direction. Then what you would want is the magnitude of the projection. I should switch back to blue. Sorry. You would want the magnitude of the projection of F onto D. That's what you would be looking for. Okay. And if you scroll up, the magnitude, right, is what we called the component, right? So this is actually what we're looking for. The component of V onto U is this right here. So U dot V over magnitude U, U is the vector in the direction that you're going, right? So how would you do it? It would be, the answer would be the projection of, nope, sorry, scalar projection. Let me erase that. It would be the component of F onto D. That would be the answer. And how would you calculate it? Well, remember, if it's in the direction of D, everything is a D except for one F. So it would be the vector D dot the vector F over the magnitude of D. And that would be it, right? U dot V over U. D dot F over D. Magnitude D. So that's what it would be. And you would have to calculate that, knowing what D was and what F was, right? So, if you wanted numbers or something, you would actually need something like this. So suppose like F was, I don't know what it is. So let's just say it's ABC, right? We just have those letters for somehow. And let's say D was horizontal. So let's just say it's pulling in the x direction, right? I guess technically we only need two. We don't need three dimensions here. So let's do AB, and then the direction, let's just say it's 1 in the x direction and 0 in the y direction, right? Because we're pulling straight horizontally, so no y component, just an x component. And what if you, the direction, the magnitude of the direction doesn't matter, so you may as well use 1 comma 0, a unit vector in this direction. That's what I did, right? So suppose the force was a comma b and the direction is 1 comma 0, then you'd be able to calculate that, and it would simply be comp f onto d is d dot f, so 1 0 dot f, which was ab, over the magnitude of d, and it turns out that that would just be a. All right. Why is it a? Because 1 times a is a, 0 times b is 0, so the top is just a, and the magnitude of the vector d, remember the vector d, I made it length 1 by definition, so that's what it is. So, it's very, I don't know, it makes sense, right? If the vector here is a comma b, if the vector here is a comma b, obviously the part that's pulling in this direction is a, and the part that's pulling up is b. Anyway, so but it does get used in physics problems because of this this idea here that if you need to find out like what fraction of force is in this direction, but it's pulling in this direction, how much of it goes in this direction, and you use a projection to find out. Okay, so those are vector projections. There is something a little bit not weird that they ask, but they do ask you to do something weird here. I'm trying to find a question that looks like it. You know what? I don't think they do. I don't think they do here. They do it in the Newton. They don't do it on the homework that I'm seeing here. So here's a different problem type. Other problem type. Okay. So they say this. They say, example. They say, no, I'm trying to think of how do they do it. How do they write it? Oh, this is really frustrating. I wanted to write it in the exact words that they use, and I'm failing here. So I'm going to have to click on the homework and find it. I can tell you exactly what the idea is, but oh well, you know what? We'll just make one up. So here's the idea. So suppose you have two different vectors, okay? So suppose you have two vectors, u, which is just a vector. So let's say like 3, 2, 5, just a vector, and another one, any kind of vector here. So let's just say 1, 2, 3. Why not? Okay. And what I want is I want to know how to write the vector v as the sum of two vectors. So I want to write v as the sum of two vectors. One that is parallel to u, and one that is orthogonal to u. All right. And the first time you see this, it just looks like gibberish, right? You're like, what? I don't even understand the question. Okay. And so here's what we're trying to do here. So you've got this vector v somewhere. So let's just say that's v, right? Now you also have the vector u. So I'll draw it like long here. It doesn't really matter which one's longer. I just always draw the u longer just because it's just easier to draw that way. So this is where you're starting, right? You've got the vector u, you've got the vector v, and they're just pointing in some direction. Okay. Now, the first part here where they say one that is parallel to u, what they're talking about is the vector projection. So this is actually the vector projection, right? Because if you do the vector projection here, right, you drop this down horizontally, you get this vector, right? And that vector is the projection of v onto u. So I'll highlight that because that's that. Now, the other thing it asks for is a vector that is orthogonal to u. So what about the one that's orthogonal to u? Where does that come from? Well, it's actually on the picture, right? It's actually this. Okay. And if you think about what you know about vector sums here, you've got a little triangle, right? And if you just think about it, I'll write it in a different color here. If you've got a v here and a projection, actually, hold on, sorry, let me erase this. If you write like an a here and a b here, come on, why can't I do this? Yeah, that's fine. I didn't actually need to redraw it the last time, I'm realizing. And a C here, right? So if you've got these vectors, A, B, and C, I just called vectors that, then remember due to vector arithmetic here, that you can see that if you add up the B and the C, B plus C equals A, right? In this picture, B plus C equals A, right? So if you were going to try to figure out what B is, sorry, if you want to figure out what C is, then C is A minus B, right? Just from the picture, or sorry, just from the line above it, actually. If you were trying to solve for this third vector C, first you write B plus C equals A using the regular rule for the sum of vectors. And then you can solve for C just by moving the B over and you get C equals A minus B. So if you want to try to figure out what this is here, it actually turns out just from the geometry of the situation that what you're going to do is it's going to turn out to be V minus that projection. That's how you get that side of the triangle. Now, if you don't know that, right, then this just seems like a really weird problem. I mean, it maybe still seems like a really weird problem. Okay, so your first step is going to be to calculate that one that's parallel, right? So the one parallel to V, sorry, the one parallel to U is the vector projection. I just put it wrong again. The one parallel to U is the projection, when I write it there, the projection onto U of V. So you calculate that. Projection onto U of V. Try to remember the formula, right? If you're projecting onto U, it has a whole bunch of U's. So that should tell me U dot V, U dot U, U, right? Everything's a U except for one single V. Okay, so let's do that. So what's U? 325. 325. V was 123, I remember. 325, 325. 325. Okay, so that's the vector projection. So we got to work this out. I'll try to do this relatively straightforward here. So let's just do the multiplications in our head here. So right, 3 times 1 is 3, plus 2 times 2 is 4, plus 5 times 3 is 15. In the numerator, 15. In the denominator, we got 3 times 3 is 9, 2 times 2 is 4, 5 times 5 is 25, 325, like that. So what do we get? In the numerator, 3 plus 4 plus 15, so 22. And in the denominator, we've got 13 and 25, is that 38? My brain's just about had it here. 9 plus 4 plus 25, yay, 38, okay. 22 over 38, of course that reduces. Does it? 11 over 19, I guess. Okay, so we got 22 times 3, 66, 22 times 2, of course, is 44, 22 times 5 is 110. Okay, so what I get is 66 over 38, 44 over 38, and 110 over 38, which can be reduced. Everything can be reduced. 33 over 19, 22 over 19, 55 over 19. Right? I think I did that right. I'm not going to check that on the computer. I'm just going to assume I'm right. So let's hope for the best. So we have that. Okay, so that's half of my answer. Now the other half of my answer is the vector orthogonal to you is simply the vector, what was it? V minus that. So the vector V is 1, 2, 3, is that right? Yeah, 1, 2, 3. 1, 2, 3 minus 33 over 19, 22 over 19, 55 over 19. So, you know, it's a little bit tedious to calculate this kind of thing, but it's not that bad. 1 minus 33 over 19. 1 minus 33 over 19. How come I'm not getting fractions on this stupid calculator? Okay, now I am. Negative 14 over 19. And then, so this is subtraction here, right? So I'm actually subtracting 1 minus 33 over 19. It's negative 14 over 19. 2 minus 22 over 19. Clear. 2 minus 22 over 19. That's 16 over 19. And then 3 minus 55 over 19, which is 2 over 19. Like that. Okay? So that's kind of an odd problem. I want to draw the situation just so we're clear here. What you've got is we were writing the vector v. So the vector v was 1, 2, 3, right? So the vector v is, hold on. The vector v was 1, 2, 3. 1, 2, 3. And so it equals the two things that I boxed. So 33 over 19, 22 over 19, 55 over 19, plus negative 14 over 19, 16 over 19, 2 over 19, right? And the idea is that this is parallel to you, and this is orthogonal to you. And there's reasons that you would want to do this sort of thing in real life, where you would want to decompose a specific vector into two parts that are orthogonal to each other. So like if you did the dot product of these two things, you should get 0. If you didn't, then I made a mistake somewhere, right? Because these are supposed to be, one's parallel to you, one's orthogonal to you, and you know that when you do the dot product of orthogonal vectors, you're supposed to get 0 by definition. Okay, so I just wanted to do one of those problems because I think there is one on the homework, and now there is simply one last question for this topic. I'm going to find it. I saved it in my photo library. So here it is. Boom. Make big. I did not make it big. Make big. So we'll solve this problem, and that will be our last problem here. So what's the point of this question? Well, let's read it and find out, right? So let's see here. So a radar gun measures the scalar projection, right? That's the COMP one, of velocity onto the line of sight of a moving object. If the radar gun gives a reading of 91 miles per hour for a vehicle measured by a police officer at an angle of 13 degrees away from the road, what is the actual speed of the vehicle in miles per hour? The motion of the vehicle is represented by the vector v. Yeah, so the idea is, let's see here. Motion of the vehicle is v, and line of sight is u. Yeah, so the idea is this, right? So like, if you're here, right, and the car, I don't know how to draw a car overhead. I didn't draw the person overhead, right? So if you have a car and it's coming straight at you, right, you measure one thing with your radar gun. But if you're like this and the car is at an angle going past you, then you measure something different with your radar gun. So it makes a difference whether it's coming straight at you or whether it's driving by you, like that. And you have to kind of know this angle here. You have to know this angle in order to deal with that, is what they're saying. Now, you don't have to really think too hard about this, okay? This is the only problem of this type on the homework, and the idea is pretty simple here. So what they're saying is this here, I think, this much, that's the shorter line. It's 91, they say. Okay, and then so that's the motion of that's the line of sight to the vehicle. So the car is like this, I guess, going this way. These are wheels. We're looking at it overhead. I don't know why we're looking at it overhead though, but we are. So it's going that way, and this is 91 mph that you measure, but this is question mark mph. Okay, so that's the deal. So in order to do this, you have to think about what is what. So first of all, if you compare this green line to this line, what you'll realize is that the top line here is supposed to be more, right? This is going to be bigger than 91 miles per hour, not smaller. Okay, so that's the first thing. The second thing is to realize that when they say 91 here, just based on the geometry, right, this is the scalar projection, not this, right? The way they drew the picture, you drop the line down and then this is a right angle. This is where the projection is. So in the picture, let me go up here for the pictures of these things. They are giving you, basically they're telling you this and they're asking for this. So they're not giving you necessarily the information that you think they're giving you. All right. So having said that, let's go up here, and we got a couple of things that we know, and probably this is the information that we want, right? This is the scalar projection, and it's equal to this. So if I just grab this, duplicate, bring it all the way down to that question here. Scroll, scroll, scroll. All right. So we have this right here. Oh no, we took the, oh, it's fine. It was a duplicate. We didn't erase it. So this is what we have, okay? And what we know here, picture, is this is 13 degrees. That's supposed to be 13 degrees. I don't know. Looks like 13 degrees. That's 13 degrees. This is component of v in the direction of u. That's right. And we also know that this is actually equal to 91 miles per hour. Okay. And what this is we want to know this length. We have the v there, and we want to know its length. So you fill the stuff into this formula, but you have to be careful about what's what. So the component of v onto u, that's the number that you actually know. So you know this side. That's what you know. So this is the 91 mph. And then you've got the magnitude of v, the magnitude of v. That's what we don't know. That's actually what they're asking, right? Like, this is v. We want to know how many miles per hour it is. We want to know the magnitude of that. So we don't know that. And then we have cosine of the angle. Well, we do know that. So this is what we actually have here. So if you solve for magnitude v, that's actually what we want. So the magnitude of v is 91 over the cosine of 13 degrees. Now, be careful, like, you're going to use a calculator, but make sure your calculator is in degree mode, right? If you're going to do this problem here. How do I do that on this calculator? Menu? No. Setup? Exit? Stuck? Exit. Setup. Why can't I? Okay, there we go. Derivative off angle radians. Okay, there we go. Oh, okay, I see. Degrees. Okay, that was harder than it seems like. I don't use this calculator. So we calculate this, and 91 divided by, that's it, 91 divided by the cosine of 13 degrees. And you get that the magnitude v is 93.4 miles per hour. Okay, and you can round that to whatever you want. And that's the answer. So the car is actually going faster. The car is going 93.4 mph. So you have to correct for that fact that it's not coming straight at you. So yeah. Okay. Now, again, they ask the same question. When I did this homework, they asked this question 5 times in a row, or 4 times in a row at least. So, refer to this and you should be good. Okay, so that's it for the dot product, I think. So we covered it enough. Again, main thing is that there's 2 types of projections, scalar and vector. You're going to get to practice calculating them, and it should be fine. All right, so that's it for now. See you in the next lecture when we will talk about the cross product, the harder one.